I will give a short talk, and then we will have some activity that will get us going. So what I'm going to present is a joint work with two of the undergraduate students that came to UNCG to work at REU, Nina Galenter from Grinnell College and Dennis Silva from Worcester Polytechnic Institute, and also a joint work with my colleague Jonathan Rowell. And so we worked and made a project on machine learning, nash equilibria, and derangements, and in particular related to the territorial radar game that we saw earlier. So the game can be described like this. I will describe the game, but for the purpose of the activity, like you may more or less forget the rules, because your task during the activity will be to devise your own game, so don't get too much influenced by what I'm showing you. But so this is the game. Like, there is a population that lives on these 6 places. Like, clearly the structure of the population is something that is important, but it's not really important for the game. You can put any graph you like. For the purpose of the game, we assume that every single place is occupied by one individual that my students nicely called blob. So I will call them blobs. So there is this blob. Every single individual or every single vertex has one blob, and those blobs, they can move. So blob number 1 can stay at vertex number 1, or it can go to vertex number 2 or vertex number 3, and it is the strategic movement. So like, blob number 1 should decide, should I stay or should I go, and if they go, then where. Clearly, blob number 1 is not the only one that decides. Like, number 2 decides, 3, 4, 5, 6, everybody decides, and so they move, and now there is a game that is played based on how they move. What Mark described were games that, once you move, you play game only with those that are there, and clearly you play the game with those that are on the place that you are in, but also your payoff can be influenced by where you are not. So for example, and this will be the case of this game, vertex number 1 is a home vertex of blob number 1. So think about maybe like state has a fishery territory right here. So if there is a lot of fish here, then the state is rich. And they would probably do better if they go to vertex number 3 to steal, or vertex number 2 to steal, unless somebody comes and raid vertex number 1 when they are not there. You can think, and we will see these cases, that blob number 1 is not really one individual. It's an ant colony that can split into many small ants, and some of them can stay here, some of them can go here, some of them can go there. And the question will be how they should split. But so for now, for the basic simple game, there is just one individual, blob number 1, and he has to decide, or it has to decide whether stay at 1, 2, or 3, and where. So if it goes somewhere, it raids the vertex. The raiding is more successful if the owner is not there, because if the owner is there, then it can kind of protect some of the resources and takes them with it. If the owner is there, or if somebody else is there as well, then they split the resources just for the sake of simplicity. There is 1 unit of resource at vertex number 1. Like if blob number 1 stays there, it takes some proportion of it, say 1/2 of the resources just goes automatically to blob number 1. If 2 and 3 are there as well, then 1, 2, and 3 split the remaining 1/2 of the resources. So vertex number 1 will get 1/2 default plus 1/6 extra. Vertex number 2, blob number 2 would then get 1/6 from number 1. And since number 3 also went to number 1, then vertex number 2 will be completely unoccupied. So blob number 1 will get all it can from number 2. So that's roughly the game. Here we have it in some details that will be then posted later. And the goal of the game is quite naturally, get as many resources as possible. So move somewhere where you can get as many resources as possible. Clearly everybody wants to do the same thing. So as we've seen before, the real game, or like kind of the real goal, is for us to find equilibrium, which is find a strategy so that if everybody adopts that strategy, then if I change from that strategy, then I'm not really making anything worse. So this is the goal for us: find strict Nash equilibrium. Now I have this concept kind of naturally falls into what Mark was saying earlier. You have a bunch of individuals that can pick a bunch of places to go to, where you can go. Now when I talked to Martin Novak, he suggested that this is just a natural thing to use machine learning algorithm, in particular multi-armed bandit. And so this is the algorithm that we used. It's XP3 algorithm. We just use XP3 because it was relatively easy to code and it was already working well. There are many other machine learning algorithms that if you just look for them, you can find many more and maybe more efficient. And so how the algorithm works? You just start with the list of possible actions to take. So for example, vertex number 1 could stay home, go to 2, excuse me, go to vertex number 2 or vertex number 3. You create a list of those actions and then you create a probability distributions. So the probability distribution will tell you how likely you are to take particular action. Now those distributions will evolve in time and they will evolve based on the past rewards. So if you are getting a good reward somewhere, then you are more likely to go there because, well, it already was working before. Well, it's quite likely that it will hopefully work again in the future. So if you are getting high rewards, you are more likely to go to that place or to pick the action again. Now, this itself would not really work well because you could easily miss something that you haven't seen or haven't experienced before. So in order to not miss any equilibrium, you mix this payoff-based distribution with uniform distribution so that you still have some non-zero chance to go somewhere where you didn't even go at all, or maybe that you went once and you got the wrong outcome or low payoff just by chance because, well, it didn't work out that time. So you create a probability distribution. Once the distribution is created, you randomly choose one of those probabilities. Like you choose your action based on those probabilities. You make the action to happen, which means that you collect payoff based on your action. Then you update the vector and repeat. And you do it many times. You kind of learn by it. And in theory, you should learn what is best. So, that has nothing to do with real learning. I mean, people would probably learn differently, but this is what we saw. It was quite surprising. There are a bunch of strategies that the algorithm described, like we ran it 10,000 times on the same scenario, like for a relatively long time, and there were quite natural six explicit peaks. It was not really sorted like this, but yeah. So this is once you sort it, and it's like this. So a bunch of the strategies like these are just random noise. Once you filter the random noise, you get these strategies. And so this was kind of success by its own. When I told my students to do this, I forgot to specify that if they do it over the course of, I don't know, like 6 weeks out of 8 weeks that they are working with me, then I will be quite happy. So I forgot to tell the timeline. So they came next day with this. Which created quite a lot of problems for me later on because
you had to find more
I had to, well, yeah. So we found the problems because they were good students. So they not only found this, but they found pattern. Yeah? So what happened is that this relatively biologically inspired problem, they were pure mathematicians in nature. I am pure mathematician in training. So we looked at patterns and they discovered the pattern, and then the rest of the talk will effectively be about the pure mathematics, but I will come back to this again. Yeah? So they discovered that there is something called graph derangement. So if you have a graph, then you have a function on the vertices that effectively permutates the vertices, but you can permutate them, like 1 can go to 2 only if there is a link between 1 and 2. And so what they discovered about all of these strategies, that they are graph derangement. So all of those all of those 5 strategies are graph derangements on that particular graph. And not only that, there is no other derangement. So what they effectively discovered was that this may be a way how to find all the graph derangements, and maybe there is some sort of correspondence between these. So we found it, or the students found this definition, and so let's just see an example how it works. Blob number 1 goes to 2, 2 goes to 3, 3 goes to 1. So there is kind of like one circle going on here, and another circle is going on here. So everybody moved somewhere, but if you can see that nobody really meets anybody else. So everybody is alone. So this is kind of funny situation if you think about stealing goods from your neighbors. Number 1 is quite successful in stealing from number 2 at the expense of someone else stealing from number 1. But well, you can think about it, that sometimes this really happens, at least in humans, like, you don't care what's going on at home, like, you are happy that you are stealing from your neighbor. So
And 3 and 4 didn't know each other.
they know each other, but so
They were nice to each other.
there is so 1 and 2 can rate each other, 3 and 4 can rate each other, and 5 and 6 can rate each other. So this is another derangement that could happen, and it was one of those 5. But so once kind of one, say when 3 decides, if 3 somehow for whatever reason decides that it likes number 1 and it's kind of keep going to number 1 quite often, then it kind of forces this cycle to happen and one of those cycles to happen. So that's kind of an artifact of the machine learning, but yeah, it happens. So this is how the derangement looks. So there is some sort of movement on the population. And well, this has no biology at all, but like it's a nice pure mathematics result that so a graph admits derangement if and only if our game has a strict Nash equilibrium. So this was something completely unexpected. Like I'm not even going to prove it in details, but like I can show it that something like that happens. So why a derangement is an equilibrium? Well, assume everybody moved, like I'm showing that they moved, and now one decides to move somehow else. So if one decides to stay home, then blob number 1 would have to share with blob number 3. Maybe number 1 would get a little bit of defense advantage, but it would still have to share, and it would definitely not get the full resource of number 2. So for number 1, going to number 2 is better than staying at home. And it is definitely better than going to number 3, because, well, in number 3, you would have to share with number 2. So you steal much more at number 2 than you would steal at number 3. So number 1 in particle cannot do anything else now. If like 2, 3, 4, 5, and 6 behave as shown, number 1 really should go to number 2. And we can kind of convince ourselves that this is the case of all other blobs. Now the same works with 4. Now the question is, can I get something else like that is not derangement? So if, for example, I have vertex that, just for the sake of mathematical notation, is denoted 0, is occupied by two blobs. It's fine, just for the sake of argument, let's assume that one of them is 0, but it's not really important. So if we calculate kind of the payoffs based on the rules, then this is beneficial for both 0 and 1 only if vertex of number 1 itself is occupied by 2 individuals. Well, none of them will be local at that time, but so this is the inductive step, that once you have vertex that is occupied by at least 2 individuals, in order for 1 or 0 to be beneficial to stay there, vertex of number 1 has to be occupied by 2 individuals. But now 2 is somewhere where there are 2 individuals, so there has to be 2 individuals at vertex number 2 and 2 individuals at vertex number 3. None of them can be listed before, and so on. So very soon you can see how it grows, and like we know that no population is infinite. So once you have a finite population, then it is clear that something like that cannot really go forever. So the only option for string equilibria to occur in this particular game is that there is just one individual at vertex. There is still one tiny feature of that can it can happen if nobody moves. This would be like cooperation, or like passive strategy. So I'm just happy where I am. I'm not moving anywhere. So this is a situation where everybody is alone on its own vertex. But this is not strict equilibrium by itself, because, well, number 1 would do much better if it decides to go and raid number 2 or 3. Because nobody would go to number 1, so resources of number 1 will stay intact, and 1 would steal a little bit from 2 or 3. So one would strictly improve its strategy or its payoff. So what we really did in this case was that we found, and this is like nice theoretical results, that like it answers the question that was over 50 years old. The only problem is that someone else answered the question 3 years sooner than us. Yeah, but it's a nice different approach to these pure mathematical questions. We kind of characterize the derangements on the graphs based on biologically motivated games, and so we found an interesting relationship. And not only that, there are some algorithm how you can find the derangements, but they are NP hard, meaning that if your graph structure has n vertices, it takes about 2 to the n steps to find the derangements. Our algorithm seemed to be finding it in much faster way, even though we didn't really test it in any significantly high vertex numbers. So potentially there is some significance how you can find derangements in a faster way, even though it is not really guaranteed. Now, this is even more biologically relevant. Very rarely you have someone that lives alone on a vertex. Like you may have a ant colony, or maybe a group. Like the whole state has a lot of fisheries right here, and the fishermen have to decide, okay, where they should fish, or the ants should decide where they should forage. If they forage home, that's good. Well, if they can steal from the others, it may be better. And so this is what we call army, territorial radar game. That you just have a bunch of army sitting here, and you have to determine how to split your units to get highest payoffs. Clearly, your enemies or the opponents are doing exactly the same thing. So if you have to optimize your strategy not only based on what you are doing or what is best for you. What is best for you depends on what others are doing. So that's kind of the fundamental feature of the game theory. So that if whatever problem you are working on has this feature that payoffs for you or outcomes for you depend on what others are doing, then there is a chance that game theory comes in play at some point. So, okay, the rules of the game are not really that important. What may be relatively nice is that we found some results that are also not really important. We can draw the results, we can draw some conclusions from them. But okay, let me show some of the results in practice. Like if you have yellow blobs here, then this is one of the potentially equilibrium strategies. Let's say if you have 10 units of the army sitting here, then for the yellow it's relatively, or like for everybody else, it is that, well, keep 6 units at home place and then just send 2 units out to explore and kind of try to steal. That's one of the potential equilibrium. There are several other ones that we have kind of found by brute force, going through every single possibility and just checking whether it is equilibrium or not. What is nice about this approach is that this black line is for the continuous army, meaning that your army is ideally divisible, so that you don't have 10 units, you have like 10 millions of units, and you can split them in basically continuum manners. Then the more units you have, the closer you get to the continuous army approximation. So this is a relatively nice result, even though we don't have it analytically. Like all numerical simulations suggest that, okay, if you really care about high number of units, then all you need to do is to do continuous army, and then it will be sufficiently close. Because finite number of armies, like anything at least for me, anything in mathematics that is finite is much harder than infinite. So that's the problem. So this is the army. So we extended the model that Mark was talking about, like to some different cases. We found that unlike in individual games, then there is some defense possible. So that was good, because if you paid careful attention, then the previous model where there was only one individual, then you effectively just raided and nobody really defended itself. But if you look in nature, nobody really does that. Everybody defends the home at least a little bit. So once we build that army model, then this is what we are seeing, that you still put something in defense. Maybe not much, but something in defense. And yeah, I haven't really seen, but so there is an effect. I haven't really shown, but there is an effect of the graph structure on the payoffs. So I would like to thank many people that made all of that possible. This was a true group work, even though the students did all the heavy lifting, and I was pleasantly happy and surprised by all the work they did. So this roughly ends my talk. I will go back to here, and so we will slowly move towards the activity. So what I'm kind of planning for the activity is that rather me trying to enforce the MATLAB on you, like you don't. there are some MATLAB files that Eric will tell us how to access, and you can access them. But you can just work on papers, or you can just work with any program that you like, and effectively your task, like you can just split into groups and try to work on something that is of your interest and maybe hopefully related a little bit to this. So I know that there are some people that are interested in fisheries, and I have tried to include like the fisheries examples right here. Like, I mean, just consider these to be different territories on the sea, and then, like, I don't know, you can incorporate the payoffs much differently than I said. Let's say, if you just fish too much at home, then maybe you overfish and then you are killing your own population. So there may be some temptation not to overfish, but like trying to fish somewhere else. Or maybe in area that maybe even doesn't belong to anybody. Like, you know, you don't know. So just come up with any kind of structure that you like, populate maybe some of the vertices any way you like, you know, try to set up the payoffs any way you like. So the payoffs may depend on who is on the vertices, who is on your own home, or like just see. Yeah? Like there can be many potential actions that you can consider, and either try to write a program or just at least write it on paper, and like I will be circling around and looking and trying to provide suggestions. There seems to be another group of people that is interested in, I don't know, group movements. So that you can take this basic game and just modify the payments in such a way that, you know, if you are alone, you have payment 1. If you are in a group of 2, your reward is 2. If you are in a group of 3, your reward is 3. If you are in a group of 4, your reward is 4, and so on. Just modify the payoff like me. You can keep the structure the same. Just modify the payoff that way, and let the individuals choose where they go. I mean, like, I don't know myself, like, where I would go, but this is the beauty of the machine learning. You know, it doesn't know itself, but like, as I have demonstrated, it just shows off. You know? So that way, maybe you will find out that just by imposing the condition that being in a group of certain size is highly beneficial, all of the individuals will somehow find a way how to group themselves without anything else. It is just because the payoffs will dictate. Or, you know, like we have talked with Garrett, like about, like, say, transmission of pigs, so that you can assume that those blobs are actually people that are trying to, I don't know, get pigs from some other neighbors. Well, actually the pigs are somehow spreading through the area, and then the question is, you know, like, if the pigs are only here, should I bring it from here? Like, you know, if I'm really forced, if I'm 3 steps away, it may cost me like 3 units of transportation costs to bring it here. So maybe it may not be that beneficial, but if the pigs are already at number 3, then it is just a small step for me, so I will bring them. And so there are plenty of potential games that, you know, all you really need is some basic structure, like a graph, then come up with some basic rules, and then specify the actions, and then we can make it work. So I will just show you one little computer program that will be available for you. That's an implementation of that machine learning algorithm. Like, if you run it, okay, and I run it quickly, so it does not really show the best results. This is just a simple triangle, and you can see that, like, 1 going to 2, 2 going to 3, and 3 going to 1 seems to be like the most prevalent thing. Like 3, 1, 2 is also good, but it should also discover, where is it? Oh yeah, so these are the only 2 in this case, but you can see that, you know, like, the others are not really that low. So if I run it more times, like this is only from out of 100 runs. If I run it more times and with slightly different parameters, then these 2 pigs would be kind of clear winners, even though right now they are still clear winners. I think it wasn't winner the last time I ran it, but yeah, so it is now. So
did it not run 1, 2, 3?
Say again?
Did it not run 1, 2, 3? 1, 2, 3 should be statically, right? 1 to 2, 2 to 3, 2 to 1.
Yeah, it is not even shown here. Yeah.
Does this mean that the frequency is 0 instead of 1?
That's kind of funny. Yes. Well, let me run it again.
2, 3, 1 and 1, 2, 3 are the same thing.
Say again?
2, 3, 1 and 1, 2, 3 are the same thing.
2,
Yeah.
3.
So that's what I figured. If they have 2, 3, 1 and 3, 1, 2, they should also have 1, 2, 3.
I'm sorry. I'm a little lost now. 2, 3, 2, 3, 1 is like 1, 2, 3 is different. Like 1, 2, 3 is like once everybody stays home. Yeah, 1, 2.
Wait, can you explain how the strategies are coded then?
Oh, I think, yeah. So, no, this is just some technical. Yeah, that's actually the biggest problem in the coding. That so once you have the actions, like this is done in MATLAB, so MATLAB just takes like action number 1, right? And then it is up to you to code that, I don't know, say 232 will somehow mean your action number 1, or so that's, I mean, yeah, no. So individual 1 has 3 potential actions: staying at 1, going to 2, going to 3. So every individual has 3 actions, which is in this case coincidental. But like in theory, you can really have, like, if you have n vertices, you can go to n potential places, and maybe if you are not connected, then your probability is automatically 0, because there is like an adjacent symmetrics that will just make it 0. And so we kept track. So this means that, like, this is the likelihood of scenario that, like, that one went to 2, 2 went to 3, and 3 went to 2. So you kind of just keep a careful tracking on how you, what number, like what number 1 of your coding means. So there is a little bit of like vocabulary that has to go behind the scene, that say if you run it as number 1, then, well, okay, for whatever reason, like this was one of the first discovered, therefore it is the first here. But so if this one was the first discovered, it would be here, and it just that, yeah, you need to have some sort of loop in the background that double checks that,
So
okay.
one is just implicit, right?
Yeah, but yeah, it should have discovered 1, 2, 3, but, well, okay, let me run it again.
It did, right? That the biggest plot right there. 1 went to 2, 2 went to 3, 3 went to 1. Right? You just did.
Yeah.
That's right. That's the 1, 2, 3.
No, this is not 1, 2, 3. 1, 2, 3 would mean staying. Everybody stays at home. It is not shown here. So this is 2, 3, 1.
Right.
So 1, 2, 3 would be.
I was saying the last.
This would be 1, 2, 3. And well, maybe it just didn't discover it simply because, well, it was never the best one. So these, okay, yeah. So these are things that the machine learning algorithm says it is the best in one run. Now, because there is so much chance, then you should not really believe. If you run it just once, it can tell you that this is the best, and like you should not believe it. Like you should run it many times and then see. And so most likely the machine learning will tell you that, well, this is the best and this is the best, and therefore, like, these two are the ones that we then considered in more details. Yes. In this case, in this histogram, is the frequency on how many times out of 100. Yeah. So you run it 100 times, and like I don't know, 26 times out of those 100, the machine learning algorithm says that this is the best one. 25 or 23 times, this is the best one, and then some much smaller number, this is the best one. And no, but this is an excellent extension, and you can definitely consider, like, all of that kind of automatic, all of that assumes that all the vertices are same. So like one potential, and like all behave like as same. Yeah. But yeah, as Eric says, you can assume that somebody is just hard-headed, and like they will stay home no matter what. Right? And therefore, this is given. It can be coded into the situation that, I don't know, just like there is just one action for that particular individual, and then all you really need to do is to see what 2 and 3s are doing, and how does it affect them. So that can be done. You can encode the fact that maybe vertex number 1 is very rich. I mean, like, there is a lot of fish here, or a lot of money here, so everybody would like to come here. Now, if you make vertex number 1, like resources at vertex number 1 very, very high, like say if these will have just 1 unit of resources, and this will have 10 units of resources, then more than likely than anything else, you will see that everybody will congregate at number 1. This is something that you can convince yourself just by thinking about it, and so that's one of the things that maybe like you can kind of test the algorithm that if the algorithm would then show, then yes, then this is what is happening. Say again?
At the lowest bar, you want 0?
There might be a mistake. Yeah, that 0 is different. Yes. Okay. Let me run it again. Yeah.
It's like, I'm out.
There are a bunch of zeros now. A bunch of zeros.
I think it's just the name you're using. It should free all the once again instead. I feel
It can mean that it just stayed home. Yeah. Yeah. So yeah, I believe that in this case that this was the convention that it just stayed home. Yeah. So you can see that I ran the same program. I didn't really modify anything. I ran it different times and I saw a different picture. But there are still the two clear winners. And yeah, so the 0 means they stayed home. So what we are not really seeing is we don't see 0, 0, 0. That's what we were supposed to see last time. I mean, well, supposed to see. Yeah, so it's never simply best strategy.
So if we were to run this 10,000 times in sort of like a,
Yeah, if you are to run this 10,000 times,
well, I guess it's not a graph.
well, okay, I cannot really show you what will happen in this picture, but like on this graph, if you run it 10,000 times, then this is what you will see. So like there will be some that are highly significant and some that are like completely insignificant. And then what you would do is that you will just say that if it is smaller than say 1%, you just call it 0. And if you do this, like you kind of put this 1% noise filter, you can say, and then you will see just these 6. And then you can kind of go back and backtrack and really decipher that whatever the strategy is, it tells you these numbers. No? Yeah. So 10,000 times is not a magic number, but somehow it is a magic number for for most of the things I do. Like it looks like that you have to do 10,000 times, and then it works. If you do it less than 10,000 times, then it's not sure. So there are, okay, there are some parameters of the algorithm that we should be aware. And okay, how can I make it bigger? At least. Okay. This. Yeah, you can. Yeah, Eric will.
I put it briefly off of our website.
And I can potentially email it to you, but it's not really ready. Like I'm not sure that I'm not comfortable putting it publicly available for everybody for everywhere. Yeah.
Requiring to use my memory. There you go.
You can email the link and then you can just copy paste.
So, I'm going to make it bigger. Do you have email Yeah. There's a way. I don't know where the Zoom is
Okay. Yeah.
on it. I'm sorry.
No problem. Yeah. yeah. So what I was almost suggest is that rather than, you know, like I can definitely go and help with this code, but and you can use this code, but it may be more beneficial if you just kind of try thinking about your own game, and then like what is posted here, this thing, this main paper, it contains the description of the algorithm, so that, you know, you should, like anybody that knows any computer language should be able to code the algorithm themselves, like in any language you are proficient with. And so this territorial radar XP3 is kind of the main source, main computer code. It, like this, his maker is just like a small routine that students wrote to produce the histograms, and rotate labels is just like a small things to make the labels a little better.
Yes, I wanted one, but then I actually, I'll show you. I actually downloaded.
So the algorithm itself has two parameters, like eta and gamma. Those parameters are not really specified what they should be. This is another thing that one should play with. Like for different situations, different numbers work best. So sometimes when you have to run extensive simulations, you have to just test it with few simple things and discover what eta and gamma is working well. And because setting eta or gamma in a wrong way can mean that you would not really see big discrepancies between the best and the not so best situations. Yeah. So I guess that I can just circle around if there are any questions or comments.